In this video, we're going to learn about power and use it in specific heat capacity problems. First, what is power? Well, it's a rate, so let's take a look at rates. Velocity is the rate at which displacement occurs. Rate has a very specific meaning in physics. Let's take a look. Velocity, that's v, is equals the rate at which, that means divided by delta t, displacement occurs. And we use S in IB physics for displacement. So velocity is just how much displacement you undergo per second. That's what rates mean. This is the definition of velocity, so sometimes we'll add a third line right here to show it's the definition. Acceleration is another example of a rate. Acceleration is the rate at which velocity changes. Let's take this statement and put it into an equation using what we know about rates. Okay, acceleration, that's A, is, that's equals, the rate at which, that's divided by delta t, velocity changes, so delta v for change in velocity. Again, this is a definition for acceleration, so we can add a third line, which we'll sometimes see. Now let's look at power, because power is a rate as well. But the funny thing about power is there's not really just one definition, there are three, and even those have some flexibility. So let's get to it. Power, that's a P, is equal to the rate at which, divided by delta t, over delta t. And now we get to the three different definitions. The first, power is the rate at which work is done. So the numerator is W for work. The second definition, the rate at which energy changes, delta E in the numerator. And the final definition, the rate at which energy is transferred, and this energy we're referring to Q, the heat. Let's take a look at a couple examples. 1,500 kilograms of water is held at an average height of 50 meters above a turbine. The water is released and rushes down, spinning the turbine and generating electricity. The water develops 1.0 kilowatts of power. This is a little bit puzzling. I don't exactly know what a turbine is, and we haven't studied it yet, so let's just see if we can keep on reading and then draw a picture. Determine the rate at which mass arrives at the turbine. This is something I haven't seen before. The rate at which mass arrives? Well, we'll just keep on going, see if we can figure out what to do with the rate there. But first, let's try and draw a picture. I know there's some water, and I know what the mass is. And I know that water is being held above a turbine, and it rushes down toward the turbine. So maybe there's a pipe carrying the water from the container down to whatever the turbine looks like. And I know how high up the water is from the turbine, 50 meters. And I know that the turbine generates electricity when the water flows down, and the power of that electricity is 1.0 kilowatts. Okay, so I'm kind of figuring out a picture. I've got my givens listed. They're in the picture, which helps. But what's the unknown? Well, the unknown, they say the rate at which, so, well, that means divided by delta t, the rate at which mass arrives. So I'll put an m in the numerator, because m is mass. So the rate of mass. Let's see if we can use our power equation to work this out. Power is change in energy over change in time, or the rate at which energy changes. In this case, we're talking about potential energy because there's height, so it's gravitational potential energy. So I've now replaced delta E with delta PE. But potential energy, that's m times g times h. So delta potential energy, what's changing for the water? The mass isn't changing. G isn't changing, that's 9.81. Oh, it's the height, because the water's flowing down. So instead of delta PE, I can write mg delta h. The height is what changes. And I even know how much it changes, 50 meters. Alright, now it's time for a fancy trick. Look at this. My unknown is mass divided by delta t. So I have mass and I have delta t, just like I need. Let me break that off to the side and write it this way. That's the same thing as what I had before. I just split off the m and the delta t. So now I can plug into this equation. I know the power. The power is 1 kilowatt, or 1 times 10 to the 3 watts. Kilo is 10 to the 3. G, that's 9.81. And the change in height, well, it's going down 50 meters. When I solve for m over t, the unknown, I get 2.04 kilograms per second. And you could work out the units and show that that's what the units are, but you also just look and say, oh, well, mass is kilograms, time is seconds, so that's our unit. Let's try another one involving energy exchanged Q. An immersion heater, that's a heater that you put into like a cup of water and then it heats up the water. An immersion heater rated at 50 watts is placed in a cup of water that's initially at 45 degrees Celsius. After 2 minutes, the water temperature is 55 degrees Celsius. So the water heated up, warmed up. Determine the mass of the water. Assume the water and heater are thermally insulated from their surroundings. The specific heat capacity of water is 42,000 joules per kilogram per Kelvin. Well, let's go through and figure out what the givens are. Well, they told me 50 watts. What's that? Oh, it's in watts, so that must be the power of the heater. So they say rated at, that just means the power of. And then they gave me 45 degrees Celsius. That's the temperature in Celsius initially at the beginning. They gave me the time interval, delta T. I know it's time because it's in minutes. And they gave me the final temperature after that 2 minutes. So that's theta final for Celsius temperature final. And then they gave me this value, the specific heat capacity, that's C. And they asked me to find the mass, determine the mass. So mass is my unknown. Now, I've been given mass, I've been given C, I know the temperatures, so I could find the change in temperature, and I know that the heat being added is Q, so I'm thinking that I probably want to use this equation to find the mass, the unknown, but let's go through and see if I can use this right now. Let's start from the right and we'll go left. Delta T, do I know the temperature change? Yes, I do, because I know the initial and final temperatures, and the change is the same in Kelvin as it is in Celsius. Okay, so I know that. What about C? Oh yeah, they gave me that. It's 4,200. Mass, I don't know that, but that's my unknown, so that's good. I don't want to know it just yet. But what about Q, the heat transferred, the energy transferred to the water? I don't have that, do I? No, they haven't told me how many joules is transferred. Okay, so if I want to use this equation, first I have to find Q so I can plug in. So how can I get Q, the heat? Well, they gave me power and time. Oh, that's what it is. I'm going to have to use the power equation, and I know power and time. So let me plug in for the power. They told me the power was 50 watts. The time they said was 2 minutes. We convert that to seconds. Be sure to convert that to seconds. So 60 seconds times 2, because there's 2 of those minutes. But I don't plug anything in for Q because that's my unknown. To isolate Q, you multiply both sides by the 120 here, and you're going to get 6,000 joules. Okay, so now that I know Q, let me make that a check in my equation. There it is. I know everything except this one unknown. One equation, one unknown. I can solve that. So I'm going to substitute in values. Q was the 6,000 that I got from before. The mass, I'm not plugging that in because I don't know it yet. C was 4,200. And the delta T is, oh, well, here's my final initial temperature. So the difference is going to be positive 10. The units are going to cancel. Kelvin and degrees Celsius, those cancel because we're talking about change in temperature. And 1 Kelvin, one change in temperature of 1 Kelvin is equal to a change in temperature of a degree Celsius. So we solve for mass, divide both sides by 4,200 and by 10, and you get 0.143 kilograms. So what did we do? What was our roadmap? Well, we had to find the Q so that we could use Q equals mc delta T. And we found Q by using the power equation because they gave us the power and the time. Whenever you have the power and the time, you can find the heat or the energy transferred or whatever else the work done, depending on which power definition you're using. You can use these equations not only can you use power with Q equals mc delta T, you can use it with m times L as well. And you can use it in scenarios where you use ml and mc delta T in the same problem. So let's say you heat some water, warm up the temperature, then you boil it. In that case, Q would be mc delta T plus ml. So it's a pretty diverse equation. We can use it in many contexts.